right, didn't receive any email requests this morning for questions to answer, so I've got the chat window open. I'm also kind of talking back and forth with some instructors on Blackboard issues. So if it takes me a minute to see your post, just understand I'm looking at Blackboard. But yeah, feel free to post any questions you have, and yeah, here for anything. fix that problem. sorry, Elijah, I didn't see you there. Markovnikov's rule and syn and anti-addition. So Markovnikov's rule says that if we have an asymmetric alkene and we add some electrophile to this, something HX, and X in this case is pretty much anything that looks like an anion. So it's an anion, it can be something like hydroxide, it can be a halide, it can be some alkoxide. It just needs to be something that when we pull the hydrogen off of it, we end up creating an anion. So the way this is always going to start is we're going to take these two electrons within the double bond, and we're going to cleave the HX bond. And this is going to do two things. One, it's going to give us an anion. The second is that it's going to end up producing a carbocation. So the question is, who's the more stable carbocation? So in the case of any carbocation, the more stable cation is the one that's more substituted. So we end up producing this as an intermediate. So we have this carbocation intermediate, and this is what our nucleophile is going to attack. So Markovnikov's rule just states that whenever we have addition across a double bond, the X group, whatever is bound to the hydrogen, is going to go to the more substituted carbon. And the reason we're going to do this is because we go through a carbocation intermediate, and this also means that we're going to get a mixture of both the R and the S configurations in terms of the final products, if we create a chiral center. Now, syn and anti-addition refer to addition relative to sides of the double bond. So if we take our double bond and we put it on its side. So we've got this molecule laying flat, and our double bond here, our pi bond is in line with the z-axis. When we have a syn, the way I remember it, a syn is same side. So in addition, we're going to get both groups added to the same side. So whenever we form a product with a syn addition, if we start with a double bond, for the syn addition, they're basically pushing the other groups down. For an anti-addition, anti implies opposite, and that's really what it means in this case. For an anti-addition, they're going to get to the opposite sides. So for our syn addition, we get this kind of cis shape with those groups. For an anti-addition, if we have our double bond, what we'll end up producing is what looks like a trans configuration. So the syn and anti only refers to how they are on relative sides of a bond. So something like hydrogenation, H2 addition. So let's say we had let's say we added hydrogen to this. If we add H2 to this with a platinum catalyst, we would get a syn addition. They're on the same side. So when we first draw our product, we had this H kind of forming this C shape. And then this hydrogen is going to push down the R2 and the R1 groups. And this hydrogen here is going to push down the R4 and the R3 groups. For something like bromine addition across the same double bond, we're going to get an anti-addition. And with the anti-addition, the bromines are going to be on opposite sides to start with. This bromine is going to push the R2, R1 groups down. This bromine is going to push up the R4, R3 groups. So the big thing with syn and anti-addition is that it has a lot of implication on stereochemistry. So if R1 and R2 are the same, or R3 or R4 are the same, it doesn't matter. But if we do create a chiral center, it's going to have strong implications about the final chirality. Because you can see, even though, so we had a syn addition and an anti-addition, even though we see the R1, R2 groups both wedge, both dash on both sides, they're actually spatially in different places. So if we were to rotate this so we end up getting this wedge dash, if we rotate along this bond, what we'd end up seeing See if I get some space over here. To get our bromines on the same side, we actually end up flipping the R3, R4 positions. So if you have a syn addition versus an anti-addition, you're going to get a switch in the groups on one side of the bond, depending on if you do anti or syn. You're very welcome. $17 to $21 the homework. Hold on, I got a quick message. Answer your question in just a minute. All right, questions 17 through 21. Let's bring up the homework. Ooh, name the following according to substitutive IUPAC naming. All right, so the longest parent chain is going to carry the name of, is going to have to carry the alcohol. So this one's pretty well worked out for you. So 1, 2, 3, 4, 5, 6. This is a hex. And let's see how it's asking you to name it. Since there is no alcohol, since there's no double bond, it's an an-all. Alcohol is going to get the lowest numbering, so we get 1, 2, 3, 4, 5, 6. So this is going to be 2-hexanol. Our substitutions here are dimethyl. And I get 5, 4, dimethyl 2-hexanol. Sorry, 4, 5. Dimethyl 2-hex. Man, McGraw, make this tedious as you can. So that is number 17. 4,5 dimethyl 2-hexanol. Question 18. Write the structural formula for a primary, secondary, tertiary constitutional isomeric alcohol with molecular formula C5H12O. So this is a linear molecule. The reason I can tell it's molecule, if we just ignore the oxygen is going to look like an H group. We have 2N plus 2. So this is definitely a saturated hydrocarbon. For a primary, we can just simply do the chain. For a secondary, we just move the OH group over. And for a tertiary, we can just kind of move a methyl group over. And these would be a primary, a secondary, and a tertiary alcohol. So the primary, secondary, tertiary here is going to refer to the same thing as those for carbocations. It's the number of carbons bound to the carbon that OH group is bound to. Is this really the right homework? Oh, no wonder this is so easy. It's test 3 material. Sorry. Let me get back to the course website. Like, this looks like a lot of alcohol stuff. Why are you struggling with this? Okay, test 4 material. Yeah, that was test 3 material. Sorry about that. Question 17. Oh, the actual homework. The following alcohol has been subjected to acid catalyzed dehydration and yields a mixture of 2 isomeric alkenes. Draw the 2 alkenes, the major and the minor product, as predicted by the Zaitsev rule. So you've only got 2 options here. So you're doing 2 elimination products. The one you predict by Zaitsev's rule is this one here, which is the 1-methyl cyclohexene. You can get elimination from the primary carbon. It does happen, but this is why it's very much a minor product. So if I draw it on my end, I won't subject you to this tedium. Because what we don't expect is carbocation rearrangement, so that's not one of the options. So I'll share my desktop with you really quick. So there's your major product. You just have what you expect by Zaitsev's rule. When you do elimination, you eliminate to the most substituted carbon. You can get some of this minor product, particularly if you go to high temperatures, but it is very much a minor product. Zaitsev's rule says that we are not likely to extract from that particular group on the ring. Question 18. The acid catalyzed dehydration of 2-methyl-2-propanol, 2-methyl-1-propanol. What carbocation would be formed at the hydride shift accompanied cleavage of a carbon-oxygen bond in the alkyl oxonium ion? So if we have 2-methyl-1-propanol, and we do acid catalyzed, and we form our carbocation, we expect, it tells you there's a hydride shift. The initial carbocation here is a primary carbocation. There's only one hydrogen to shift from. So your initial carbocation is this kind of like, well, it looks kind of like 3 tiers of the plus. If you had a methyl shift means that this group moves over. So if we did a methyl shift, we would get this one here. So a hydride shift is a hydrogen shift. A methyl shift is a methyl, means the methyl group moves. And then it asks you for part 2, which pathway do you think will predominate, a hydrogen shift or methyl shift? We'll compare the carbocations. This is a tertiary carbocation, this is a secondary carbocation, so it's more than likely that we're actually getting a shift to a hydride shift because this will create the most stable carbocation. Question 19. Predict the product of the following reaction. You have methoxide in DMSO. The thing here is that big bases eliminate, small bases substitute. So my first impression would be that you would actually end up getting the substitution reaction. And in something like DMSO, you're going to get a symmetry inversion. So the Cl, we have a methoxide attack to displace the chloride. And so I would say that's your first product, would be the ether. So let's see if I'm right. It's not the substitution product, so the next option here is elimination. So the elimination product here would form a double bond here because there's no hydrogen to abstract here. So let's edit the structure and see what that looks like. That is the correct answer. For some odd reason, it's using a tiny base. It would use terpene oxide in this case. So the question I ask you next is, which hydrogen do you expect it to extract from in order to make this reaction occur? So we've got 2 hydrogens here, hydrogen A and hydrogen B. And what we want to do is we want to eliminate the hydrogen that is opposite the chlorine. So what's going to happen is that our methoxide is going to attack the hydrogen. The hydrogen is going to give its bonds to the double bond, and then we're going to get extraction of chlorine. So what we expect is that HA is the one that's removed, the one that is on the opposite side of the bond from the chlorine. So And the term here is anti-periplanar. HA is removed because it is anti-periplanar to the leaving group. Yeah, I don't particularly enjoy that term, anti-periplanar, but the big thing here is anti. It is anti to the chlorine. Because it is anti, they'll be on opposite sides. Question 20. Draw the mechanism for the following reaction. Tert butoxide attacking 1-bromo, 2-methyl propane. So what occurs in this reaction is that our lone pair attacks the hydrogen, the bond breaks between the hydrogen and the oxygen, goes between the chlorine, and we extract the bromine. So if I draw my reaction mechanism arrows, and I'll share it with you on my desktop so you can see what I've drawn, hopefully. So I've got this bond going from the oxygen to the hydrogen, between the hydrogen bond to the carbon-carbon bond, and breaking the bond between the carbon and the bromine. Hopefully this works. Yep, so that's the mechanism. All right, question 21. Using curved arrow notation, draw the mechanism for the formation of the given alkene product. So we have hydroxide extracting doing elimination to give us, oh, it's actually a pretty straightforward mechanism. I was expecting something far worse. Okay. I actually kind of did you a favor with this drawing. So with all elimination reaction mechanisms, particularly using strong bases, we have attacks on the hydrogens that are opposite whatever the leaving group is. We draw the arrows from between the bonds, between the hydrogen that's being extracted and the carbon, to the bond between the carbons, and then we get rid of the bromide. So I'll put it back to the desktop for you. Tells you to finish the structure. So we're going to draw our bonds from the lone pair to the hydrogen, from the bond between the hydrogen and the carbon to the bond between the two carbons, and from the bond between the carbon and the bromine to the bromine. And that's it. So those are questions 17 through 21. You're welcome. right. If there aren't any other questions, thanks Elijah for asking quite a few questions today. Fingers were a little tired from climbing this morning. I will see all of you, some of you tomorrow. Remember that we're doing the pilot labs tomorrow. If you can't find the resources, they're on the course resources under quizzes and assignments, under lab assignments. And yeah, see some of y'all tomorrow.